Good afternoon. Sorry I don't speak Turkish, even though I've been coming here for 12 years. I'm going to talk about some of the solutions for geothermal resource exploration and development management risks and challenges. And I want to talk about the fact that I think Tevik covered some of these things, so I may skip some topics as I go through. But these solutions lie in optimizing, the solutions of optimizing geothermal project success lie in data-driven decisions. And we can use those to optimize resource use and minimize the development risks and costs. It's a kind of technical risk mitigation facility that can go along with the financial risk mitigation facilities that a lot of you are familiar with. In this talk, I want to present the importance of making the decisions with data, some of the methods we use, and try to emphasize that these risk reducers are applicable to both the financial side of the industry, developers, and also government regulators. Identifying and discovering, confirming, producing your resource is one of the biggest costs in a geothermal project. It's also one of the biggest risks. And we can reduce those costs, though, I think, by reducing or managing the risk. And we're going to focus in this talk on technical ways to do that, but these complement the financial risk mitigation. How do we go about minimizing resource-related costs at each stage of a geothermal project? We focus on developing the data and information that will inform our decisions. And we do that by collecting and analyzing relevant resource data, collecting enough data and of sufficient quality so it's useful. And we don't stop when the power plant goes online. I think it's important to learn from the mistakes of others. Sometimes in Turkey we get a little isolated in our geothermal development. We have a lot of unique aspects to the geothermal projects in Turkey, but we can learn from other mistakes. Geothermal is an international industry, and a lot of people have stumbled over some of the things that we're working on here in Turkey before. So I hope by the end of the talk you have some sense of the risks, but also you can see that there is a method to the madness. There is a way that we can address these risks, and we've worked pretty hard over the years to reduce them. Just a little bit about the talk. I'm going to introduce myself, talk about the stages of development, which Tevik touched on, some of the resource challenges and how they present project risks, and then some of the solutions in a case study or two. I'm Jill Haizlip. I've been working in geothermal for over 30 years, in all aspects from the early research stage to development, including 12 of those years, mostly in Turkey. I've worked around the world, though, and I am working now in lots of different places. It gives me a perspective on some of the projects here and their issues. I've also worked not only as a consultant, but as a developer, and that also gives a little different perspective. I've worked on solutions to big problems like how big is the project, but also some detailed projects in corrosion mitigation, gas handling, and hydrogen sulfide abatement and scaling and things like that. I'm the founder and owner of Geologica. We do exploration, resource assessment, reservoir modeling, development planning, well testing, resource design criteria, and monitoring management programs. So we'll talk about some of these as we go forward, but I just present this because I'm talking from experience. Some of the talks we heard before, way up here in terms of geothermal, but we're talking about on-the-ground experience, getting your hands dirty kind of application to the helping projects be more successful. Stages of projects that we're going to talk about are identifying the project, you know, at the should I get this lease stage, exploration, discovery and confirmation drilling, a resource assessment and feasibility study, finance, project, EPC, wellfield development drilling, that's the development project, startup and commissioning, and long-term sustainable operations. I won't go through this in detail, but at every stage there's a resource issue that that presents a risk and a challenge, and also there's a solution. You know, in the beginning, when you're identifying your license area, there's a due diligence methodology, and we do that before we buy the license area if we can. That's a great way to reduce risks or spending money that then you don't have to work on the project. When you get into the exploration stage, what is the risk? That it isn't there, or it isn't big enough for what you planned. Well, there's a method for exploration in geothermal that's, or there are methodologies used all over the world: geology, geophysics, geochemistry, and we really focus on developing a conceptual model of the field that then drives those exploration phases to be focused on, is there a geothermal system? If it's there, how big is it? How hot is it? As we move, if it's a yes and we want to start drilling, we target that well based on our conceptual model. The risk is, of course, that the first well is a failure. How do we mitigate that? By using the best methods to target the well and to drill the well. Similarly with confirmation, your next 2-3 wells, but the important thing is to collect enough data as you're drilling and testing those wells, so at the end of that confirmation stage, you know if you have a resource and you can define it well enough to move to the next stage, which is the resource assessment. Because if you can't, and you try to design your project in your feasibility study, and there is too much uncertainty, that feasibility study is going to have some holes in it. And the risk there is either you can't finance it because you don't have enough information and the banks or the investors won't think it's unreliable, but the other risk is that you finance it and you move forward with a project that isn't right and ends up failing. So as we move on, and similarly, the resource presents risks during the design phase, and then startup and commissioning involving matching the design to the resource. You can't match the resource to the design. The resource is what it is. It's set by Mother Nature. We can't change it. So the one thing you can change is the design of the project, not just the power plant, but the gathering system. And so that's where to make the change, not the other way around. In terms of long-term sustainable operations, the risk is, of course, that you can't operate your power plant at full load. That can be because you didn't design the project to the resource, but it can also be because you weren't monitoring and managing your resource and paying attention to the changes and making those kinds of reservoir management decisions that can maintain your resource over the life of the project. I'm going to skip the next slide because it's just a different view of what we just talked about. This is a view of the relationship between risk and cost. So early in a project in geothermal, the risk is highest, but the expenditures are lowest. That's when to spend a little money to reduce risk. That's when your information is the most valuable because the risk is highest. And these numbers across the top are decision points at which you can say, I'm not going to do this, or I'm going to do it differently. And at each one of those decision points, you can recoup your costs, or at least decide not to move forward. And notice that they all come before the cost jumps up. The cost being on the left, and the risk being on the right. These two plots, one is from SMAP in 2012, and the other is from a US study in 2008 by the Department of Energy. And the absolute numbers may not fit your project, but I'm almost certain that the trend of the risk and the cost are the same. This is another view of the same idea, and I'll skip that. One other thing I wanted to mention is these are absolute numbers on the costs at different stages of a project. You can see that they start really low, but in Turkey, it's rare that people are spending on early studies and exploration $2, $3, $5 million. And maybe every project doesn't need that much expenditure, but it certainly shows that there's room for additional evaluation, data collection, and science early in the stages of a project. Here's a plot of the different aspects of geothermal from, can you see that? No, I don't. There's no pointer. Think you have a pointer? Anyway, from the left, it is early stage geology, geophysics, to conceptual modeling and drill targeting and your drilling plan. Obviously, the costs go up as you. Okay, thanks. As you move across, how does that work? Oh, okay, sorry. So all this up to this point is before drilling. And in this, we got up to $1.5 million. That's a relatively small amount when you understand that after your drilling and testing program, up to the feasibility study, we're at about $13 million. And so the issues are, you're spending a small amount of money early on. It's your opportunity to increase the quality of your project and reduce the risk by collecting step by step the data you need to make the decisions as you move through the project. I'm going to go through those stages real quickly and then get to a case study or two. Just the challenges and solutions from each one of those stages. When you're starting out, the challenge is, does this license area have anything? Is there a geothermal system there? And the solution is to do due diligence before you start. There is a certain geologic setting you have to have a geothermal system. You have to have heat, you have to have permeability, you have to have water, and usually you have to have some kind of seal or protection. And you also have to have local conditions conducive to development and the correct environmental conditions for a development. And if you don't have those, all those things, it still doesn't say you have a successful project, but at least you have a chance. And there's no point in developing license areas if you don't have a chance. In exploration, the challenge is that you can't collect enough or reliable enough data to characterize your resource and develop a conceptual model so that you could target your discovery well. What's the solution? Focus on the exploration methods that are appropriate for your site. I'm going to talk a little bit about this project in Nevada. It's in the basin range of Nevada, which has been probably the closest corollary to the geothermal systems in Turkey, outside of Turkey. It's an extensional basin. There's no volcanic heat. The original surface exploration in this area was done in the 1970s. Then they drilled about 35 shallow temperature gradient holes, some deeper holes, and did a little geophysics. They found a shallow outflow zone and about 175 degrees C zone at 600 meters, and a deeper, hotter zone in one well at 1,000 meters. In 1991, they drilled a couple additional holes that were successful, and they built a 2.5 megawatt binary plant after they proved 6 megawatts. This is a standard rule of thumb. You have 50% under the wellhead, you can build your plant. Then they drilled 7 dry holes right near the discovery well. The plant has never gone online because they've never had enough fluid and temperature. So that's the risk. So then what did they do? Fortunately, they used a lot of persistence and continued to explore and do an extensive amount of interpretation using reflection seismic and some new satellite imagery. And they developed a new, I didn't show you all the old conceptual models, but frankly, they didn't have any when they did the first drilling, but they developed a few, and they ended up with a conceptual model that you can see has very narrow fault-based upflow. So if you don't hit that fault, you're not going to get anything. And they finally figured out that this deep, the higher enthalpy, the over 200 degrees C reservoir, and now they can target some wells. This is a flat view of the anomaly, the entire anomaly, and this is this cross-section. So we think the lack of early stage conceptual model really limited the type of resource, and the exploration that they did was very shallow temperature gradient holes. And the shallow outflow zone that covered that huge area masked the deeper variation in anomalies. And you know, somebody financed that power plant and all that drilling. Somebody else did it. They put a lot of their money into it. I don't think they asked enough questions, and they didn't have the data to rely on, even if they'd pushed those questions. So the next stage of drilling, discovery and confirmation drilling, what are the risks? That the wells aren't hot enough, they don't flow enough, you have a drilling failure. The other risks are there wasn't enough data collected to evaluate, so when you get done, you can't site the next well. Or For confirmation drilling, there wasn't enough data collected to do a resource assessment and reservoir characterization, so you can't do a feasibility study and you can't finance your project. So solutions: build a strong conceptual model, target your first well on it, update it as you drill, collect a lot of data when you drill and when you test, and do high quality testing. Tevik touched on this. It's really a critical aspect to geothermal development. And as you can see, I've mentioned some of the kinds of testing. We do pressure temperature surveys, pressure temperature spinner surveys, flow testing, buildup, interference, tracer testing, drawdown, buildup tests, gyros, geochemical sampling. All these things are important, and they have to be analyzed and integrated back into your conceptual model. Just what kind of data did you get? A critical thing is to remember that your project is good. The preliminary design of your project is going to be done based on the testing of the first few wells. Because the way geothermal projects work, you drill a few wells, then you do a preliminary design and finance it. And if you don't collect enough data, you can't do that preliminary design. And if you're really off and you finance that, then you have to either refinance or change, and that costs money. So a lot of these risks we talk about, we're not talking about risk of entire, some cultural failure. It's risk of things costing more than you planned. And most projects fail because things end up costing more than you planned, so do your testing, develop a good test plan, and don't skimp on the testing. Skimp on, maybe something else, but this is not expensive compared to even drilling one more well than you have to. Single well tests, you get productivity of a well. Another important thing is, when you have lots of wells, you need to do multiple well tests and interference tests and understand the reservoir. A single well tells you well capacity for that well. Multiple well tests tell you about the reservoir. And that's what you're producing over time. Not one well, you're producing the reservoir. Okay. So the risks of a feasibility study, or resource risks related to feasibility study, are that the resource wasn't correctly assessed, your project doesn't match the resource. In a feasibility study, you should be able to characterize the resource in terms of the total capacity, but also what is it like? How much gas? What's the enthalpy? What's the best separation strategy? How many wells do you need? Where should the injection be? Where should the production be? What's the deliverability curve? All of these things are required to be determined from those first few wells, and they go into the feasibility study, which then goes into the financing. What kind of solutions? Collect enough data, collect good enough data, use international standards, require QA, QC, do duplicates, do it again. Evaluate your confidence level. The developer and the financial industry needs to ask a lot of questions. Be self-critical, make sure that you have confidence and that you've covered all the aspects of design from scaling to enthalpy to mass flow. They're all important. I think I'll skip through this. We've gone through this, but every aspect of every one of these questions that are part of the resource design criteria. The resource design criteria is what the engineer needs to know to do that design. And we have tests for most of the things. You just need to take the time to do them. During the project design, what is the risk? You turn it on, it doesn't operate at capacity. Either the power plant doesn't or the gathering system doesn't. You have to spend a lot of money to fix the problems. And what I find is the project design engineers rely on the owner to provide those resource design criteria. So as an owner, you need to do your homework and have the data for them. I'm going to talk a little bit about Kizildere. These are slides presented in the Geopower Turkey conference in 2011. Kizildere has been, and I think someone's going to talk about this power plant tomorrow. It's owned and operated by Zorlu, by MTA, or the Turkish government since the beginning in the early 70s. It's purchased by Zorlu in 2008, and they went about expanding and upgrading the original plant. It's in the Menderes Graben with lots of other projects. It's a layered reservoir, so that provided some extra challenges. The upper layer is 190 to 200 degrees and has about 1.5% gas in the reservoir, and that mostly supplies Kizildere 1. The deep reservoir is hotter, gassier, and mostly supplies the 80 megawatt Kizildere 2 triple flash binary plant. This just sort of shows some testing we did to confirm the layering and the depths of layering. These are temperature static to the extent we could, and you can see that they're not all in equilibrium, but these are static temperature logs. We had a very low, high temperature gradient, which means high change in temperature versus depth. This is an area where there's no permeability. When you have permeability or circulation, usually the temperature log goes vertical. And then we have another conductive layer and another vertical. And the depth of these is different. Throughout the reservoir, it's not a flat, but this is the upper reservoir. These represent these flat or low gradient sections represent the separation between the upper and lower reservoir, which we know isn't perfect, but it occurs in a lot of places enough to protect this deep reservoir and the difference in the temperature and gas, at least in the initial state. This is the original development, ejection on the east, production on the west. This is the Kizildere 1, which is the original development. This is the Kizildere 2 area, injection and production. What were the resource challenges and solutions? We're trying to produce Kizildere 2 from a deep, hot reservoir that underlies another reservoir. So we have to go through that permeable zone and set casing in that little section in between the two. That was one challenge, and the drilling engineering department there did a good job of setting the casing through that first zone, but not after the first well was they tried to produce in both. That didn't work too well. We also had very high non-condensable gases, and that was managed through the power plant design. Calcite scaling in the wells was pretty severe, and that's been managed by downhole injection of scale inhibitor below the flash point, which is very deep in some of the wells, and it's been a challenge managing that for the resource group at Zorlu since. We established sufficient production at startup, and we haven't had to do a lot of extra work for that, at least not in the immediate time after startup, because we did a lot of flow testing and multi-well testing, and we had the advantage of 20 years of production from the first plant. Even though it wasn't the same reservoir, we learned a lot. And so Zorlu successfully brought that plant online 80 megawatts in 2013. It's just a picture of flow testing. We spent a lot of time. This is a lubricator with the scale inhibitor so we could run a long-term test. Silencer, weir box, flow line. We take the sampling occurs off the flow line. In sustainable production and injection, the challenges are that we can produce and inject the required mass flow, enthalpy, and chemistry over the life of the project. And we have, this requires maintaining your reservoir pressure and temperature. It also requires maintaining your well integrity and diameter if you have scaling over the life of the project. Well, what can you do? As we mentioned before, you can design the project for the resource, not try to fit the resource to the project, and then you can monitor the changes and manage the reservoir. There aren't that many things you can do, but you can move injection, you can move production from well to well. I've just wanted to show this slide of from a manager of a plant in Mighty River in New Zealand. And these are this is a company that has some of the biggest and longest operated geothermal projects in the world. Wairaki came on in the 50s, and they still are struggling with some of these problems. But one of the first things is matching above ground equipment, meaning power plant and gathering system, to below ground. That's what engineers call the reservoir, the below ground stuff. And, do field testing. But as they mentioned, that's a snapshot. You design your plant, and then you have to run it for 30 years. So make sure you pay attention to the changes as they are developed. One more case study I'd like to go through. It's also something that started out as a problem and became resolved through a lot of persistence on the team running the project. It's also in the western U.S., Basin Range. This could be in Turkey. If you closed your eyes and didn't look too hard, it could be here. It's a non-volcanic, fault-bounded system, has a metamorphic basement rock, which is the primary reservoir rock, just like many of the systems here in Turkey. It's blind, no hot springs. It was discovered because they were exploring for minerals. There is some surface alteration. They drilled some slim holes, did some aeromagnetics and other geophysics, and drilled 2 discovery holes in the early 2000s, which found about 170 degrees C, pretty shallow, 1,000 meters plus or minus. They did some detailed fault studies, which led to a conceptual model which suggested there was upflow along the range front fault, which is equivalent here, we call it the Graben bounding fault. And it, based on a first few production wells, they developed a conceptual model with production in the east and injection in the west, production next to the Graben bounding fault, and injection further out into the basin. They built a 45.5 megawatt gross binary plant and commissioned it in 2009, 6 production wells, 4 injectors. In the first couple of years, temperature declined by 10%, power generation a little more, and that decline continued for several more years. They got a new owner in 2013. They intended to apply some well stimulation methods to increase production. But, so this is the original. Yeah, I'm almost done. I want to give the happy ending. So this shows the power plant here was here. Here's the injection wells, the production wells. This is the Graben-bounding fault, very similar to a lot of projects in Turkey. Here's a conceptual model which had the fluid coming up and out along that fault system, not just one fault, but a series of parallel faults. They did a bunch of additional work. First, they tried to reduce flow from the coolest well, then they drilled new injection wells, and megawatts were still decreasing, so they thought they needed a new strategy, and they went back and developed an entirely new conceptual model that suggested that all the production was along two faults, and they were actually injecting on the upside of a fault, and the water was just running down and cooling all the injectors. So they revised the injection strategy and used some idle wells, some of those early discovery wells, and now they're closed these injectors, and they're just trickling water into these other injectors. Although the temperature has slowly gone down, it's starting to stabilize, and the megawatts have been stabilized since 2013. So it was a little difficult, but they did figure it out. It took them 4 years, but they're now under stable operation. And I think this is an important lesson because a lot of people think that the projects fail because of overproduction. It's not always overproduction. Sometimes it's just well field design, injecting and producing from the wrong place. So I think I'll stop there. Thank you for inviting me here. Thank you, EBRD, for having this. And thank you, the geothermal industry in Turkey, for a lot of years of good work, and getting to know Turkey has been a pleasure.
Şimdi yarım saatlik bir kahve aramız var. Ondan sonra tekrar ikinci oturumla devam edeceğiz.